Now, let me talk about in certain details what we meant by non-metallic inclusions, what are the types of inclusions, wherefore they are coming. I have mentioned that micro inclusion basically means which we cannot see under, or rather with normal eye, these have to be seen under the microscopes. So, normally they are of the size range of 1 to 10 micron, and our resolution of eye is 100 micron, 0.1 millimeter. So, these size of inclusions which are called micro inclusion we cannot see with normal eye, they have to be seen under the microscope. What are the different techniques and all, we will go into the details later on. But what is important here is what are their sizes, what are their distribution, what are their chemistry, what type of inclusions are there, what is the amount of inclusions. Now, they have influence on the grain size, they might control the grain size in the steel, they might create or generate other phases, certain cases, as they may act as the nuclei for other phases to form. They might influence the mechanical properties, like they might increase the strength, they might decrease the toughness, ductility, similar properties will be affected, or even other properties like creep might be affected in presence of inclusions. Okay, there are certain mechanical properties we might be affected, we will take up later on. Now, these are products of metallurgical processes. Example is deoxidation. That means these are getting generated during the metallurgical reactions during steel making. As I have told you, we have to take care of dissolved oxygen in steel by deoxidation. How do we do it? Either we use silicon, ferrosilicon, ferromanganese, or we use aluminum. So, in that process dissolved oxygen will come down. How dissolved oxygen will come down? In the form of SiO2 might get formed, MnO might get formed, or aluminum oxide might get formed. So, these inclusions, that means these oxides, they are part of the metallurgical process. So, we call it deoxidation products. So, these are small non-metallic inclusions. So, we might get complex oxides, we might get sulfides. If we have more amount of sulfur in steel, we might get and we have manganese sulfide, we might get manganese sulfide in steel. Manganese sulfide, as I have told you, is presence of manganese sulfide is better than iron sulfide, because iron sulfide has low melting point, it might call incipient fusion, the melting point of the steel comes down, there are many difficulties, many problems. So, manganese sulfide is better than iron sulfide. So, if you have manganese in steel and if you have sulfur in steel, normally some of you might be knowing that we have to get manganese amount in steel, say manganese by sulfur amount in steel, say more than 25. So, manganese by sulfur ratio, many people will tell has to be more than 25. Why? Because if you have high amount of manganese in steel compared to the sulfur, then manganese sulfide will be formed, iron sulfide can be taken care of, there will be no iron sulfide. So, these inclusions basically are sulfides, complex oxides, or oxysulfides. These are micro inclusions. Now, I have talked about exogenous entrapments, they are large in size. So, micro inclusions are small in size normally, which are metallurgical products coming out of the metallurgical reactions like deoxidation during steel making, but exogenous entrapments which are basically what? I have mentioned some of them, like slag from ladle. All of us know that during steel making stages, like we have liquid steel, we also have slag. What is slag, by the way? It is basically the combination of oxides. Like basic oxygen furnace, we have a lot of iron oxide, we have some calcium oxide, we have silicon oxide, we have manganese oxide. So, that slag we do not want to get entrapped in steel because of certain issues we will discuss later on. But these slags, whether it is from the basic oxygen furnace or from ladle or from tundish or from the mold basically means it may be a continuous casting mold, it may be a ingot mold. where some slag is forming because we are adding some powder which forms a particular slag, mold slag. So these slags, whether from ladle or tundish or mold, should not get entrapped in steel, because these are slags are basically what? These are basically oxides, different types of oxides, either calcium oxide or magnesium oxide, or some extent manganese oxide, to some extent iron oxide. There can be sulfides, because when you are removing sulfur, sulfur go to the slag. There can be calcium sulfide, there can be fluorides, like in mold slag, in tundish slag there can be some fluorides. So all these constituents might create problem if they are getting entrapped, and interestingly they are large in size, unlike micro inclusions. Reoxidation product, we have talked of deoxidation, which are relatively small in size. But what are the reoxidation products? When does it form? We have made a very good steel using secondary refining. Now the steel, if it is exposed to air, air contains oxygen and nitrogen. So we have a lot of reoxidation, we have a lot of renitrogenation in steel. So the steel surface has to be always covered. It should not be open to the air. It should never be exposed to air. It has to be covered with slag, or whenever it is coming from one vessel to another, like at the time of casting it is coming from the ladle to the tundish or tundish to mold. During the transfer from one vessel to another, this has to be covered with some refractory nozzles, so that it does not get exposed to air, because if it gets exposed to air, reoxidation products will form, renitrogen products will form, which are particularly reoxidation products like oxides. You have aluminum in steel, we may have titanium in steel, we have of course have iron in steel, we have silicon in steel. So reoxidation products can be alumina, can be silicon oxide, can be some to an extent iron oxide, can be titanium oxide, you have titanium in steel. These will create a lot of problems, and please try to remember these reoxidation products like alumina, titanium oxide, they have very high melting point. So at steel making temperature, some of them are solids. So this will create a lot of problems. This will create nozzle blockage during casting. So we have to be very careful, and their sizes are quite big. We can see these reoxidant products with our normal eyes. That means they are more than 100 micron in size. Then refractory erosion products. From the refractory lining, erosion might take place, because the liquid steel is always in motion. There are certain velocities of liquid steel. So if the refractory component is not good enough, their strength, high temperature strength is not good enough, there might be some erosion. So this erosion might get entrapped in steel, refractory erosion. What are these basically? There may be magnesium oxide, there may be some carbides, there may be alumina. These oxides constitute what are the refractories. So these might get entrapped in steel. So exogenous entrapments can be slag from ladle tundish mold, this can be reoxidation products, renitrogen products, or it can be refractory erosion products. So all these exogenous entrapments, when they are present at a size of large dimensions, they are harmful. Harmful from the point of view of quality of steel. Why? They might affect the property. Also they might create unseemly surface cracks or surface defects on the steel component. So these are really bad. Now let us talk about these NMIs, non-metal inclusions. I have told it can be sulfides or oxides or whatever, oxysulfides. Now the sulfur content of steel is normally known from the analysis. That means when you are analyzing the steel, we know whether the sulfur content is 015, 01, 005 or not. We know certain applications for which sulfur has to be less than say 01 or 005 or even 003. So we know if the sulfur is more, the sulfide inclusion also will be more. So from the sulfide point of view, we have some idea of how much of sulfide will be present in steel from the analysis of steel, sulfur analysis steel. If we know the sulfur is less than 0.005, we know the sulfide will be quite controlled in steel. But what is happening with the oxides? Oxygen content in steel at the final stage, that means when you have do all the refining, we are casting, at that stage normally oxygen is not measured. Oxygen in steel is not measured, like sulfur, phosphorus, nitrogen, these are measured in steel, carbon, these are measured in steel as part of the steel chemistry, but oxygen is not measured in steel. So how do you know how much of oxide is present in steel? We can know this if we measure total oxygen in steel. We know that oxygen is present either in the dissolved state or as oxides. I have mentioned that dissolved oxygen is quite high when you have just finished the steel from melted the steel in BOF or electric arc furnace. There the dissolved oxygen is as high as 500 ppm, 600 ppm, 700 ppm, but we do deoxidation. Any good steel has to be deoxidized, that means the dissolved oxygen comes to less than 5 ppm. In the process what is happening is dissolved oxygen is coming down, but oxide is getting generated. Unless we reduce the oxide content in steel by allowing them to float up and get dissolved in the slag, there will be some oxides in steel. There will always be some oxide in steel. Our aim will be to control the amount of oxides within limits. So the total oxygen is basically oxygen present in dissolved state plus oxygen present in the oxides. Now if the dissolved oxygen is very low, then if we know the total oxygen, say total oxygen is 30 ppm, and we know the dissolved oxygen after good killing is less than 5 ppm. Dissolved oxygen incidentally is possible to measure in steel at the time of steel making. So it has been found that whenever we are doing good killing, dissolved oxygen is less than 5 ppm. So now if you want to measure the total oxygen, so we know that if the dissolved oxygen is less than 5 ppm and the total oxygen is 30 ppm, so the oxide inclusion will be around, or rather oxygen as oxide will be around 25 ppm. So we get an idea of oxide cleanness in steel from total oxygen, because dissolved oxygen is low, so most of the oxygen is present as oxide. So we must measure total oxygen in steel to understand how clean is the steel. As I have told, the NMIs basically are two types, one is the oxides and is the sulfides. How much of sulfide is present, we can know what is the sulfur content in steel, but normally we do not measure total oxygen in steel. But if you know what is the total oxygen in steel, that means we should measure total oxygen in steel in a good quality steel. We can also know how much of oxygen is present at oxides. That gives an indication of the oxide cleanliness in steel. So this total oxygen after refining, that means the final stage of refining at the time of casting, if we know the total oxygen, if we measure total oxygen, this can be taken as measure of oxide cleanliness. This is very, very important, and we must remember to measure total oxygen in steel. Now this is an important issue. I have told that no steel is free from inclusions. Now 1 kg of reasonably clean steel, can you imagine how many inclusions will be there? I have mentioned here 10 to the power 8. So many inclusions are present in 1 kg of reasonably clean steel. It is not a dirty steel I am talking about, I am talking of clean steel, reasonably clean steel. Fortunately, out of these 10 to the power 8 inclusions, very few are of larger size. Majority, 99% out of more than 99% are very, very minor size of small sizes. Around 400 out of these 10 to the power 8 inclusions are 80 to 130 micron, only 10 are 130 to 200, maybe 1 only is about 200 to 370. So the volume fraction of small benign, we call it benign non-metallic inclusions. Small inclusions means benign, they have less deleterious effect in steel, so these are benign. So the volume fraction, the number of these benign inclusions are more in steel. So, we are fortunate enough that way, but few large non-metallic inclusions, they are harmful. We have to be careful about the large inclusions in steel. Now, the detection of these large inclusions are difficult, because you know what are their volume fraction? Very low, much low, maybe 0.01 or maybe 0.001%. So, it is very difficult to find these inclusions in steel. I will come to this aspect later on, how to find inclusions in steel, but the detection of the macro inclusions are difficult. But it has been found that if the total oxygen content after refining is less, that means oxide inclusions in general are less, then also these macro inclusions will be less. This issue will be taken up in greater detail later on, but I am trying to harp on the issue that total oxygen, if you measure in steel at the final stage of steel making stage or just at the time of casting, then we know that if the total oxygen is less than say 25 ppm or 30 ppm, then oxygen as oxides is less, that means oxide inclusions are less. So, the steel is relatively clean with respect to oxide inclusion. If the sulfur is less, steel is relatively clean with sulfide inclusion. So, this is a relatively clean steel. So, I have talked about what are the defined types of inclusions, talked about what are minor inclusions which are formed during the metallurgical processes, what are the large inclusions or exogenous entrapments which are coming from either slag during steel making stage that getting entrapped, or from refractory erosion products or deoxidation. So, we have to be careful about the exogenous entrapments in steel, because these exogenous entrapments only lead to large NMIs which are really harmful. Again and again I am repeating, the minor inclusions which may be present in steel in large numbers, they are benign, they are less harmful, they are of no consequence to the steel properties or the surface quality of steel, but these large inclusions are really what are harmful. Thank you very much.